All right. Let me start by asking if you have any questions. So there seems to be no further questions. I will continue with another very important signal. We have seen one important signal, which was unit step in the previous hour. Now, the unit, let me go to back, unit impulse is our new discussion topic. And unit impulse is a difficult signal, but it's a signal that we must be very much aware of. Its notation is delta t, and the way we are going to draw it on the time axis is an arrow, an upward arrow, is a little bit thick arrow like this to distinguish between the vertical signal axis and the signal itself. Let's draw this a little bit thicker. Okay, that thick arrow pointing upwards is an impulse. What makes it a unit impulse is when we put a 1 here, for example. So we indicate that it is a unit impulse. Mathematically speaking, it's a dangerous signal. It's awkward because this 1 does not mean that the height of the signal is 1. In fact, the height of the signal, if you are drawing it as a continuous time signal, when you're drawing it that way, the height of the signal is infinity. But so what is this 1? It's the area under the impulse, like this. From minus infinity to infinity, delta of, let's say, t, dt, which is the integration of this signal, the delta signal from minus infinity to infinity. This is equal to 1. So the area under the signal is 1. But it has infinite height, and the width of the signal is 0, technically speaking, in such a way that that 0 width times infinite height, which gives you the area of that rectangle shape, is 1. So how can we come up with such a thing, and why are we using it? The way we come up with is to start with d of t, which is equal to, let's say, 1 between minus 0.5 and 0.5 and 0 else. So let's use this auxiliary signal d. And when we draw it, it actually looks like this. From minus 0.5 to 0.5, it is 1. So this rectangular box is d of t. How can we make this narrower and taller? And the narrower it gets, the taller it gets, so that the area underneath still remains to be 1. So in the limiting case, we will squeeze it so much that its height will blow up to infinity, but the width will shrink down to 0. So the way that we can do it, for example, is something like this. We can think of lambda times d t over lambda, for example, for instance, where lambda is some large number. If it is 2, for instance, when lambda is equal to 2, so lambda is equal to 2k's, it would become like I have confused the multiplication with a summation, it's not lambda is equal to 2 case, it is lambda is equal to 0.5 case. So I have to erase this. Sorry about that. I'm trying to obtain this when this is 0.25 minus 0.25 and 0.25, and this one becomes 2, where the area is still equal to 1. It is narrower, but twice narrower, but twice taller. But lambda is equal to 0.5. Okay, so there seems to be a confusion on my side, not your side, regarding the definition, because the definition should also change. So I'm correcting it. It is 1 over lambda d t over t times lambda. Yeah, let me put it that way. Probably I did not change anything. I just reverted all the operations. Lambda times t. I'm not very comfortable with dividing the t operation, because when I'm dividing with something large, it's actually corresponding to multiplying with something smaller, but nevertheless, I want to do it this way. Okay, now with lambda is equal to 0.5, probably this was already what I previously wrote. And now, as you see, as lambda shrinks down to 0 this time, 1 over lambda will blow up. It will be going to infinity, and d of lambda times t will become smaller and smaller and smaller. So this is how we approach the delta t. Delta t is equal to limit as lambda goes to 0, let's say d sub lambda of t, which is making it narrower and taller. We cannot really draw this like a regular function. We cannot draw an infinite value. We cannot put an infinite value at t is equal to 0, but we can draw it using a particular notation or a way of drawing it like this. Okay, we put an arrow and indicate that the area underneath is 1. And there is a certain relation between this impulse and the unit step. And it is this. The impulse is actually the time derivative of the unit step. You remember the unit step? It was an abrupt increase to 1. When you take the derivative of that abrupt increase, the time derivative at that changing value will be infinity. So that infinity is the infinity value of this impulse. And as you see, it is symmetric. The impulse is made from a symmetric rectangular pulse by making it narrower and narrower. So the integral of delta t will give you u of t. If delta t is the time derivative of u of t, then u of t is the integral of delta t, isn't it? It's the fundamental theorem of calculus, the inverse relation between a time derivative and time integration. So let's now integrate delta t. But we have to be a little bit careful here, because this integration has a limit from minus infinity up to a time instant. So the upper limit of this integral is t. So from minus infinity to t, we have to integrate delta. We have to integrate delta of t. But we cannot call it delta of t now. T is in the upper limit of the integral. So we have to use some other terminology. The best terminology that we have available for such mathematics in Signals and Systems we also use it that way. Whenever we need an auxiliary time variable, instead of t, we have to use something. What we will use will be the Greek letter tau, which is actually the Latin letter t in Greek. So tau is this, okay? Delta of tau d tau. So I'm integrating the delta function through the time index up to a t. And how does it behave? Let's analyze. The impulse is here, and this is the tau axis, and I'm integrating along t. Let's first give a t which is less than 0. Let's say that this is t. So when I integrate delta of tau, the impulse shape, from minus infinity up to t, all the way from here to here, what is that integral? That integral will be 0 because there was nothing. So this will give me 0 if t is less than 0. Whenever this red t stays to be less than 0, this integration will give you 0. So now let's move this t up to a point exactly here, 0. Over there, what will be the integral? So now I will show it here. This is where t is, and I'm integrating. When I integrate, everything up to here will be just zeros. And at this point, the integral will give me the area under half of the rectangle. And no matter how narrow that rectangle is, half of it will give you an area of 0.5. So it is 0.5 when t is equal to 0. And whenever t moves further to here, now the integration will be all the way from this point up to this point, okay? All these places that I am just indicating, they will give you a 0 integral. They will not contribute to the area underneath, except the impulse itself. And what's the area under the impulse? It is 1. So the area from minus infinity to this new t point is 1, the area under the rectangle, remember. Now, don't you remember that this last thing was indeed the definition of u of t? So this derivative and this integral formulas are essentially inverses of one another. Therefore, we will say that in impulse is the time derivative of a unit step, and the unit step is the integral of the unit impulse. So it's a sharp, very tall signal. What are we going to do with it? Well, we are going to use it. That's why we come up with this delta of t. We will use it all throughout this course. It will be perhaps the most used signal in this course. It is helpful for, by the way, I have to give you a few more versions of delta of t. For example, how can we plot delta of t minus 5? If x of t is equal to delta of t minus 5, what does it mean? It means it's an impulse at 5. This is x of t on the time axis. This is how we are going to use it. And if x of t is equal to, let's say, 3 times delta t minus 2, for instance, then the way to plot x of t is At 2, we will draw a taller impulse whose value is 3 this time at 2. This is x of t. So these are shifted or scaled impulses. And the scaling is not the infinite height. It's the area under the impulse becomes 3 now for the last example. Okay, that's how it happens. And it can be negative as well. For example, minus pi times delta of t plus 1. It is an impulse at minus 1. Delta t plus 1 is an impulse at minus the magnitude of minus pi. And therefore, the area underneath, when you integrate, will give you minus pi. Now, what are we going to do with it? We are going to use it for sampling or picking a value of a continuous time signal at a certain point. For example, suppose that x of t is equal to t times u of t, or 2t times u of t. First, you should be able to understand what this signal is, how that signal behaves. So you must visualize it in your head, or you should be able to draw it, which is the same. How can we draw this? X of t is equal to 2t times u of t. Because of this times u of t, it is zeros until this point. And at this point, after this point, the function becomes 2t. So it is like this, blowing up to infinity with a slope of 2. For example, at 1, the value here is 2, and at 2, the value here is 4, vice versa. Right? It goes on like this. This is 2t times u of t. Now, suppose that at a certain point of a, all right, what is the value of the signal? We know that it is 2a because the function is given to you. But for any x of t, the way to find x of a, which is this point, the way to find it is by sampling that point. And we sample any point on the signal, on the function, is using impulses. And we do it like this. We first multiply x of t by, if you want to sample at a, then you have to multiply it with delta t minus a. So what happens here? You're multiplying an impulse with a function. When you multiply any function with an impulse, you get an impulse because the impulse is 0 everywhere except that instant. So after the multiplication, it will still be an impulse, but the magnitude of the impulse will change according to the value of the signal at that point, at the corresponding point. And the magnitude is the area under the impulse. And in order to determine the magnitude, you have to integrate the impulse, the resulting impulse. And that will give you the corresponding value of the signal at that corresponding time instant, which is x of a. So this is how you find x of a, technically speaking. X of a is x of t times delta t minus a integrated, where you find the area underneath. It's like sampling x of t at t is equal to a and picking that value, this value here. All right. So we are going to use impulse like this for multiplying with signals and therefore determining the values of the signals at that time instant. You can change a to any value and it will just sample at all different values. That's the way that we are going to use. For the time being, we have to also understand what happens when you scale the time in impulse, and that is a problem. What I mean is this. What is delta, I'm sorry, for example, delta 2t. Normally, delta 2t is twice squeezed version of, or x of 2t is the twice squeezed version of x of t, right? That's the way we squeeze the impulse, or the functions. But you cannot squeeze an impulse because impulse already has a zero width. So delta 2t is actually twice narrower version of an already zero narrow function. But remember these approximations. If you make this one, for example, with an area of 1 underneath, twice narrower, what will be the area underneath? The area will be not 1 anymore, but it will be 1 over 2, because it is narrower with the same height. So when you squeeze in time, you don't really squeeze in time, but actually change the area underneath. The area under the impulse changes. And delta of 2t is becoming 1 over 2 delta of t. It's a pity, isn't it? You are trying to change or scale in time, but actually that happens to be, that converts to be a change in the magnitude. But this is what happens. Conversely, if you divide t by some number, delta, for instance, t over a is actually a times delta t. If you do not understand why this happens, then you have to just accept and apply it like a formula, which I hate to do. But I think you can understand it by squeezing the rectangular box, the finite impulse, which is not really the impulse. The impulse is in the limit, but think of a finite box. And if you squeeze the box or extend the box, its area, the area under the box changes. And that area is here, as you see. And it is still delta of t. You have to apply it as delta of t. So these are the things that you have to be careful about while dealing with impulses. You should better try not to apply a scale in the time of an impulse. Okay, that's a bad idea. And if you have to just do it, then please do it like this, as I'm doing. Squeezing in time means shrinking the area under, and extending in time of an impulse means actually increasing the area under the impulse. Signals did we come up with, and how can we notate them in general? Please take note of these notations. I'm opening a new page now. We have seen a couple of important signals. One of them, or one class of them, were periodic signals, sines and cosines, but we already know them. But in continuous time, these signals are the important signals. One of them is the unit step. So unit step is this. Sorry. It's this. This is u of t. Okay. Which abruptly increases to 1. The second signal that we have to know, or let me write the notation here, it's the u of t. The second signal of interest is the impulse on the time axis. This is delta of t. Now from here, we can make shortcuts to communicate with each other and to ask questions. So when you see that kind of a notation, you will understand what I'm telling you. Another commonly used signal is a unit ramp signal, which is zeros here and then with a slope of 1, it increases. So x of t is actually t times u of t. And in the book, they give a name to this one. They say this is r of t, which is the ramp. Let's write the names. This is impulse. This is step. What other things can we think of? We can think of a rectangular box from minus 0.5 to 0.51. This, they usually use rectangle of t. For a box function.
Hocam sayfayı biraz yukarı alabilir misiniz rica etsem? Şu ilk yazdığınızı görememiştim de.
Okay. You mean go down like this?
Evet. Teşekkürler.
Okay. That is okay. That's unit step, the first one, and then the unit impulse, and then the ramp function, and then the rectangle box function. In the book by Oppenheim, the notation for this one is like a strange calligraphic pi of t, because pi is like a box, you know, so maybe they have chosen that notation. But don't worry, if it's an exam question, I will explain, I will explicitly write what I mean by saying these things. But it's always a good idea to know already the notation. The other one is unit triangle, like a rectangle. Now this time it's a triangle. But the triangle is actually from -1 to 1, like this. And notice that the unit rectangle and the unit triangle has unit areas underneath. The area under them is 1. And the notation of this is a capital lambda, because a lambda is like a hat or a triangle, as you see, of t. This is the triangle shape. Of course, it is zeros after and before mine. This is 1, top value. These are standard signals. I'm not really using the rect or at least the ramp and the triangles. I don't really use them. I indicate them in many cases, but the rectangular box is sometimes used. So I may be using them because the transform of it or the limiting cases of those rectangle functions, they are important. Of course, we have other signals which I don't really need to draw, but because it's obvious. One of them is this signal like this. -1 for negative time and +1 for positive time. And we know that it is sine, the signum function. But it is a function that we have been knowing from the high school anyway. So we don't need to really deal with it in a lot of the cases. Now, the next thing that I should be talking about would be convolution. So let me write in capital letters. Convolution is an English terminology which means we are entangling, doing things with two entities. For example, two strands of hair may be convoluted with one another and it's very difficult to separate them, okay? It's like entangling two things. We will be entangling two signals, of course. And one of the signals will correspond to the behavior of a system. It is the definition of a system. And the other one will be the input signal. So we will be entangling the system definition, which is explained in terms of a signal, and the input signal. We will entangle them in such a way that the entanglement output, the convolution output, in other words, will give you the result of the system, the output of the system. when the input is X, and when the system is described by the second signal H, X convolution H will give you output Y. That is an operation that we will be using for determining system output. But of course, it is a general way of, a general mathematical way of putting a formula. We are going to convolve two signals to produce the convolution output. And for that, it's critical to understand how the signal can be separated in time. How can we one by one analyze a signal in terms of a combination of very dense impulses. We will have separate impulses, and when we combine those separate impulses, it will form the signal in the limiting case. Of course, the impulses must be very near to one another, continuously changing the impulse locations. So we have to come up with an integration definition, which is like the Riemann sum or the Riemann way of integrating a single valued continuous function. Have you ever heard of, from calculus, did you see the Riemann sum approximation of integrals? It's like there is a smooth function, but we put very narrow rectangles, and we just add up the area under these rectangles, and the narrower we make those rectangles, the area of those rectangles sum will converge to the true integral of the continuous smooth function. So such things are necessary to make an introduction to this convolution business. I'm telling you these because it may be a relatively bad idea to start it now and continue for 5 minutes. I don't want to do that, so I will stop at this point. But before stopping, what I will tell you is that I will I will advertise some other videos on the internet before coming to the Wednesday lecture. On the internet, please try to find continuous time convolution. One alternative is my own lectures, because I have given the link from the Canvas system, or on Facebook, you can find them, or they are YouTube videos. Just try to watch them. Try to watch the corresponding convolution explanation video. Try to find it. It may be a little bit after, a little bit further discussion than our current situation, but regardless of whatever it is, try to find it. And then I will explain again on Wednesday. You can also try to find it from other resources as well. There are excellent videos on the internet, which are having very nice technologies for writing on the screens and things like that. And they are native English speakers, so their way of explaining things is even better than mine. Of course, better than mine. So you may find them more understandable. So please do that before coming to Wednesday lecture. Try to learn it by yourself. Try to understand, and then we will make a refreshment. And I am sure that when we do it that way, you will better understand and learn, and not forget, because it's like learning it twice. And in the next time, we will be dealing a little bit the convolution integral and its extension to continuous time convolution. Probably on Wednesday, I won't be still doing continuous time convolution, but we will be doing the so-called convolution integral, or convolution sum for discrete time signals, to express the signal. Without expressing the signal, without putting them on the time axis, it's impossible to make convolution. First, we have to expand it on the time axis. We will see how to expand it. But we don't have the time for that for the time being. So we will do it on Wednesday. and hopefully we will continue with the important topic of convolution. You may remember in the first quiz, or you may not, because you couldn't. Some of you guys couldn't just see the questions because I made them hidden. That was a mistake. But the first quiz was asking you questions about the things that you may come up with in the examinations. You may go back to the quiz if you wish. Maybe now they are visible. I don't know. The questions, I mean. The first question was regarding determine the convolution or determine the output or things like that. So it's a very obvious exam question. So you have to know it. You have to make exercise of it. But first you have to learn it. Try to learn by yourselves from the videos first, and then we will continue on Wednesday and continue in the next week with those important topics. So I will stop now. I'm not going to do any further content, but you may ask questions if you have.
Sir, I wanted to ask a question about books. I tried to get the book, but I wanted to ask, will you escape any chapter of the book or any portion or section of the book? Because
So,
I'm gonna...
okay, I will stop the recording if you don't mind.